Okay guys, welcome back. Last time I actually saw you in person, we covered the section 4.9 and began 5.1. Last week you worked on the 5.1. I had 2 videos and some handouts. Yesterday you worked on that quiz. Hopefully you have turned all of that into me. If you have not sent me pictures of any of your work, please do so. Also, if you're having questions or issues, do not hesitate to contact me. Okay, I'm here to help you in any way that I can. I want to go on and start section 2 today. So we are going to be talking about definite integrals now. This video is going to be very similar to all the things that you were doing in 5.1. So it should just continue with what we were looking at. We're just seeing a different notation. The third handout in 5.1, you were taking a problem and you had to do the sum of those rectangles, which we looked at, and then you were doing a limit as n went to infinity to get the true area under that curve. Well, what we're seeing now is I might write it like this. This curved sign, it's like a tall skinny S, that's called an integral. From A to B. A is your lower limit. B is what's called the upper limit. F of x, that's our function. Sometimes you'll hear me call that the integrand. It's the thing we are integrating. Now I'm aware you guys don't have notes printed out for this, so if I were you, I would just write down this equation here. The integral from a to b of f of x dx equals the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I star times change in x. Write that down. You might write down what I'm writing here in blue, just so you know when I talk about the lower limit or the upper limit, which pieces I'm referring to. So the only difference with what we are doing today, we're still calculating the areas under curves, but I will present the problem to you differently. Okay, pause this if you haven't had enough time to write this down. I want to go ahead and start an example. I'm actually going to skip this piece. We've already talked about that. And I just want to go right into my first example. So this is just to help us get used to these notations. When I give you something like this, and if I ask you to write an integral, so this is basically saying your original equation is represented by this. We are finding the area between these numbers. So this would be the integral. Your lower limit is the beginning of that interval, so from -3. Your upper limit is the end of the interval. So 2. We're finding the integral from -3 to 2. Now we need our equation, which is this piece. This x sub I, don't let that confuse you too much. Remember, we did the summation stuff and we wrote formulas that had i's in them. When you see this x sub I minus 1 or anything like that, that's just going to get replaced with an x. So this is just 2 minus 3x. That's the original equation we were looking at. And this change in x, we are going to call that dx. Anytime you have an integral symbol, you will always have the dx at the end. Okay. So the handout I'm going to be giving you after this, the first 5 problems, are just taking this limit notation and rewriting it as an integral. And I'm not even having you calculate anything there. That would be your final answer. Let's do a couple more. So I want this as an integral. So we do the integral. This is your starting and your stopping point. So from 0 to pi. My equation is this, but instead of x sub i's, we just use x. So x sub I cubed will just be x cubed, plus x sub I is just x, sine of x sub I, that's just sine x, the change in x at the end gets replaced with the dx. I'm going to throw one more up here because I put some on the handout like this. A little later in this video, I'm going to talk about midpoint sums. We've done over and under estimates, and I talked about those as really left-hand and right-hand sums. We can also look at midpoint sums, so you might see something like the limit as n approaches infinity of the sum from I equals 1 to n of, let's say, okay. If I give you this, I'm asking for the integral from -1 to 4. When you see this m sub I, that's really the same as an x sub I. M just represents midpoint. So when we go to write our equation, that will change to an x as well. So it's the integral from 1 to 4 of the cube root of x plus 4. And instead of changing x, we put dx at the end. Alright, so that's like the first 5 problems on your homework. Just going from the limit to the integral notation. Now what I want to do is actually evaluate some of these integrals. So let's say I gave you this one. I want to use the Riemann sums like we were doing in the last section to evaluate this integral. So the first thing you need to do is find your change in x. I didn't specify how many rectangles we were looking at. So if I'm looking at this, we're starting at 0 and ending at 4, so our change in x is just 4 minus 0. If I said I want 5 rectangles, you divide it by 5. I didn't specify, so we're just going to divide it by n rectangles. So this is 4 over n. Okay. So if I am looking at a limit here, my x sub I is just your starting point plus your change in x times I. Are you on the first rectangle, second rectangle, third rectangle? That's what the I represents. So in this case, it's just 4 over n I for our change in x. So if I want to do my Riemann sums here, it's like the third day handout. We are doing the limit as n goes to infinity because I want the true area here of the sum from I equals 1 to n of f of x sub I. Okay guys, what I'm using right here is this one definition that I have you wrote down. The integral is the limit of the sum of f of x sub I times the change in x. So I'm just using that formula. So f of x sub I, we are plugging my x sub I into this equation. So it will be 4 over n I cubed minus 2 times 4 over n I dx gets replaced with the change in x, so that's 4 over n. Okay, simplifying this mess. So I've got limit as n approaches infinity, sum from I equals 1 to n. Okay, this would give me 4 to the third over n to the third, I to the third. minus 8 over n I. This is all still times 4 over n. So if you distribute that, 4 to the third times 4 would be 4 to the fourth over n to the fourth I cubed minus 8 times 4 will give me 32 over n squared I. Okay, and you're welcome if you want to go ahead and evaluate 4 to the fourth, that's certainly fine. Okay, so now you use those formulas. The I cubed formula is n squared times n plus 1 squared over 4 The I formula is n times n plus 1 over 2. Okay, I really actually didn't need my summation right there because I added those up. I used my summation formulas. Okay, so now looking through this, I want to reduce as much as I can here. I could cancel an n squared, I could cancel a 4, so I get 4 to the third over n squared. And if I took n plus 1 and FOILed that out, that's n squared plus 2n plus 1. And again, we canceled this 4. Minus 32 over 2 would give me a 16. Could drop one of those in, so 16 over n. And that's just n plus 1. Okay. So if I distribute this, 4 cubed is 64. The n squares would drop on this first term. Okay. 64 times 2. So, or you could think of that. Your 4 to the third times 2, if you kept it in that other notation, that's just your 128. One of those ends cancel. Okay, this time 4 to the third, so 64 over n squared. Minus, this time distribute a negative 16 over n, times n would be negative 16, minus 16 over n. Anything with an n on the bottom just goes to 0. So this is 64 minus 16, which gives us 48 for our final answer. So this might seem a little similar to the third day handout, that 3-question handout that we were doing last week, where you were just finding the sum and then at the end you took the limit of it. Okay. This is a little more tricky, so I do want to practice a few more of these. Feel free to pause the video and give yourself some time if you need to. Okay, so my first step, I like to find my change in x and my x sub I, and that helps me a lot. So your change in x is just your ending minus your starting over n. So that would be 2 over n. Your x sub I is your starting point, so 1 plus your change in x times I, because you have to add that change in x every time. So we are going to do the limit as n approaches infinity of the sum from I equals 1 to n. Again, this is from that first line definition you wrote down in your notes. Tells you what the integral is equal to. The limit of the sum of f of x sub I times the change in x. So my f of x sub I is going to this equation, replacing your x with your x sub I. So x sub I is 1 plus 2 over n I squared minus 4 times the change in x, which is 2 over n. I recommend simplifying as much as you can. So if you FOIL that out, you get 1 plus 4 over n I plus 4 over n squared I squared. We still have our minus 4 on the end, times that 2 over n. So if we distribute the 2 over n, we get here. You could combine like terms, you could have done the 1 minus 4, we can do the 2n minus the 8n. That just might make our lives a tad easier. Now I'm going to do my summation rules. So my limit stays, but my sum is going away because we're actually evaluating that part now. This doesn't have an I in it, so it's like a constant. If you add up the constant every single time, remember you just multiply it by the number of times you add it up. So we're starting at 1, ending at n, so you just have to take it times n. Plus 8 over n squared. Okay, now we're adding up I. Remember your formula for I was n times n plus 1 over 2. Plus 8 over n cubed, I squared. So the formula for I squared was n times n plus 1 times 2n plus 1 over 6. So those are the formulas from section 5.1. If I start simplifying this, negative 6 over n times n is negative 6. This one I can cancel one of those n's. 8 over 2 will be a 4. And you can go ahead and simplify that more. I'm just trying to be very clear in what I'm doing, so I'll come back and do that. I can cancel one of these n's. 8 over 6 would give me a 4 over a 3. I'll go ahead and FOIL those two parentheses, so you get 2n squared plus 3n plus 1. Okay, distribute the 4 and divide by n. So 4n over n is 4 plus 4 over n. Okay, I'm going to distribute my 4 and divide by 3n squared. So 8n squared over 3n squared would be 8 over 3. 12n over 3n squared would be a 4 over n. And a 4 over 3n squared. Okay, we know anything with n on the bottom goes to 0. So we have -6 plus 4 plus 8 over 3. So -2 plus 8/3 is a positive 2/3. So the area under that curve between 1 and 3 was a positive 2/3. Okay. So this is just writing it and then taking the integral, writing it back in the notation from last week, and then using the summation rules to simplify. The last piece that I want to talk about here is the midpoint rule. So let's look at an example. I want to find the Riemann sums for this equation, taking the sample points to be the midpoints on the interval 0 to 3 with 6 rectangles. Okay. So we are starting at 0, we are ending at 3. And we are dividing this thing into 6 rectangles along the way. If I were asking you to do a left or right hand sum, or the over and under estimate, the first thing you did was find your change in x. So 3 minus 0, we're splitting it up into 6 rectangles, so that's 1/2. If I said I wanted the left hand sum, then you would use 0, 1/2, 1, 1.5, 2, and 2.5. If I said I wanted a right hand sum, that means for the first rectangle, you would use, oh my goodness, I can't draw, the right hand endpoint. So the first point you would use would be the 1/2. And then the 1, 1.5, 2, 2.5, and this time you'd end at 3. If I ask you for the midpoint sum, that means the value you use is the middle of each of these rectangles. So if you remember, we just added up the areas, length times width. All of these have a width of 1/2. And then we just took our x and plugged it into this equation. So if I were asking for a left-hand sum, the first thing you would do is put in a 0. If I'm asking for the midpoint, between 0 and 1/2, the middle point is 1/4, or 0.25. So I'm going to put in a 0.25 for my x. We should have 6 of these because 6 rectangles. To get your next point, once you have the first one, all you have to do is add your change in x. So if I'm at 0.25, add 0.5, so the next one is 0.75. Add 0.5, so 1.25. Add 0.5, so 1.75. Add 0.5, so that's 2.25. Add 0.5, so 2.75. If I added 0.5 again, I would get 3.25. That's outside my interval. I already have my 6 pieces now. So now this is just a matter of calculator. For the sake of time, I'm just going to tell you it comes out to be a negative 0.703125. The negative tells us this is below the x-axis. Positive areas are above the x-axis, negative are below. Okay, so just like the over and under estimate, or we could call them left and right hand sums, the difference is if it's a midpoint, you take the middle of each rectangle along the way. Okay. Let's do one more of these. So I wrote it in the interval notations, or the integral notation. My change in x, this one, it would be 2 minus 1, but I'm splitting it into 5 rectangles, so we get 1/5 or 0.2. That's how much we go up every time, but keep in mind you're starting at 1. So your first rectangle starts at 1 and ends at 1.2. So if you're doing the left-hand sum, you would use the 1. If you're using the right-hand sum, you'd use the 1.2. For the midpoint, we need the middle of those. It's like the average, add them up and divide by 2. So 1.1 will be the first thing I use. Okay, area of a rectangle, length times width. All of these have a width of 0.2. So I'm going to plug my 1.1 into my equation. So 1 over 1.1. Plus, I should have 5 of these. You add 0.2 each time, so the next one will be 1.3.
Mom, pictures I want them snails.
Next 1.5, 1.7, and 1.9. If you put this in your calculator and add it up, you should get 0.6919. Okay guys, I know this was a little bit longer video. We are not done with the section, but I am posting a handout to go with this on Classroom. You have today and tomorrow